Welcome. In this lecture, we shall be doing a few more problems using the root finding methods. But in this lecture, we shall be looking into some problems which have a set of equations, and that I have also told you in the class that when we have a set of coupled algebraic equations, how we deal with them. And we shall be talking about nonlinear algebraic equations. So, first we shall take an arbitrary problem here. So, I have not mentioned any kind of physical problem associated with this, but let me tell you that such kind of problems you often encounter whenever you are trying to have multidimensional flow, or you have coupled momentum transfer, heat transfer, or momentum transfer, mass transfer, or coupled heat transfer and mass transfer. So, what happens in those cases that you write the balance equations for momentum transfer, for mass transfer, and for heat transfer, and then you find that all these equations become coupled, because for example, in the heat transfer you will find the velocity is coming and the velocity is obtained from the momentum transfer, and again in the momentum balance equation you may find the various properties which you are using, they may be varying with the temperature. So, you need to know temperature at each time instant, and those temperatures should be obtained from the energy balance equation. In similar fashion, you may also find some dependency of the momentum or the energy or enthalpy on the composition of the particular system, and in the composition itself again will be dependent on the velocity profile or the temperature profile in the system. So, in this manner you find a coupling is generated between all the three types of transport phenomena, and on top of that if you have some kind of reacting term which gives rise to some generation or consumption term, you find that the problem becomes further complicated. So, instead of taking those real life problems, what I have done is this, that I have just demonstrated the use of our methods of finding the roots which we have done earlier for single equations for a multivariable system with this particular problem, and you can easily extend it for any other kind of real life problems. So, here we have just taken these two equations only, and whenever we have two equations it becomes quite simple in terms of solution, but please understand that in real life you may be having more than two unknown variables. So, here we have these two methods to be used here, and let me tell you that here we have shown these two f1 and f2, and these two y should be the vectors. Okay, they are vectors, because this y vector is nothing but the vector of the y1 and y2. Okay. So, this is basically vectors. So, if we put these two equations together, it will be another vector f, which is a function of y vector, okay, and this is basically we are trying to solve it to be 0, and f is equal to this f1 and f2 vectors. Okay. So, that is how we look at this particular problem. Now, first we try to implement this successive substitution method for this system of equations. So, here we write that we have to first find out the values of this y1, y2 from these two equations, and please always read this y as y vector. I am not putting the arrow all the times over this particular y. Okay. Now, we can use any of these two equations to generate an appropriate expression in terms for y1 and y2. Here I have shown one way of finding it out, you can have your other way. Like here we are taking from this particular equation, we are finding the value of y1, and from this equation we are finding the value of y2. Okay. So, you may try some other way, that you may find y1, here you have what we are doing, that we have y1 we have taken with this particular expression and y2 from this expression. Okay. Another way, that you can also take it to be a cube root. If you take this particular term on the right hand side, then you can easily see that y1 may be taken as this particular this term divided by 2 and cube root of that. Okay. So, that may be another way of finding this y1. I am just writing for you here, like I can take y1 to be 4 minus 8 y1 plus 4 y2 and cubic root. Okay. So, this may be another expression for y1, or you may even use this particular expression to get the value of y1. Okay. So, you have many choices for this y1 and y2. For your understanding, I have just taken one of the choices. So, here we have for y2. Okay. And what we are doing now, because this method needs some initial guess values for bracketing the root. So, let us assume that y1 0 and y2 0 are like this. Okay. Now, please understand that we have to bracket with respect to both y1 and y2. Okay. So, what we do here? So, we take this particular problem. In this problem, we choose these two equations for demonstration purpose. Now, please understand that when we have only two unknowns, the things becomes much simpler to find the value of these roots, and understand this. In these cases, this y is basically a vector, and this y vector is given by y1, y2, or is something, it can also be written like y1, y2 transpose. Okay. So, this T is the transpose. Similarly, this f1, f2 vector may be written like this, that I can define another vector f, that will be equal to f1, f2, or same as f1, f2 transpose. Okay. So, these are various representations of these vectors, and from now on I won't be writing y with the particular arrow. We shall understand by default that we are talking of a vector y. Now, coming back to the problem. In this problem, we find that we have two unknowns y1, y2, and for this particular method, what we need to do is this: we have to represent y1 and y2 from these two expressions. So, for example, I have taken these two expressions for y1 and y2. I have found the y1 from the first expression and y2 from the second expression. For your convenience, I am giving you another option of choosing the y1, like from this equation I can choose the y1 like this, that means I take the cubic root. So, this may be another way of representing the y1, and similarly you can do the similar thing for y2 for this expression. Also, you may get y1 from this equation and y2 from this equation. So, there may be multiple ways of choosing the expressions for y1 and y2 from given set of equations, and in my lecture I have also given some condition so that we are going to have convergence, so that we do not have the instability problems in the solution. And with this particular given choice of y1 and y2, what we are going to demonstrate is that how we can proceed with the solution. So, as we have understood that for this particular method, we need some initial choices of y1, y2. So, here we are choosing these two values like 0.5, 0.5 for both the unknown variables. Now what we do, we take the first equation, the expression to update the value of y1 and we just plug in the value of y0. This shows that we are putting all these inside, whatever is there inside the bracket at the 0th level. So we put the 0th level values over here and we update the y1 value to this value. So we can see that 0.5, it has moved up to 0.5875. And next what we do for y2 also we update it, and what we find that we are getting 0.4885. Now please understand that depending on which expression you are taking, this direction of the movement of these roots will also change. Now after this we can now move on to the second iteration. What we are now do, we take the updated value of y1 and y2 and we again find updated value of the y1 and now it is coming to 0.6299, and similar thing we do for y2 and we find it is coming to 0.4858. It seems that if you look at these two expressions, it seems that for y2 with this particular choice we are able to converge faster than for y1, and it is very much possible that different roots will converge at different rates to the solution, and then whenever you are checking for convergence, you have to check for convergence for each of the roots separately. Okay, and whatever convergence criteria you may evolve, that must take care that all the deviations for all the roots are taken care of, and the precision and the accuracy must be ensured for all the roots involved in a given system of equations or a given process. So here you can see that the roots for y1 with this particular representation is not converging so fast as it for y2. Now you can keep doing this particular process and till you reach convergence. Next we come to the implementation of Newton-Raphson method for the same set of equations. You may also wonder that why I am skipping for the second or the regular fallacy method. Please understand that those may also be implemented, but their implementation becomes a bit more involved, so that for multi component system or whenever we have multivariable systems, we generally do not adopt those regular fallacy or the secant method. We rather go with these two methods which I have demonstrated in this particular lecture. And now we go to the Newton-Raphson method, and as I showed you in my lecture, in this case the y will be obtained like this, that we have a particular Jacobian. For your recollection, I just write that this is the Jacobian matrix, and this is the matrix of the partial derivatives. Okay. So we need the Jacobian in whenever we have multivariable problem for Newton-Raphson method, and then what we do that we find this Jacobian from this expression. That means we have to take the partial derivative of all the functions with respect to each of the unknown variables. So in this case we have two unknown variables and two functions. So this will be reducing to dou f1 by dou y1, dou f1 by dou y2, and dou f2 by dou y1 and dou f2 by dou y2. So that means it is giving rise to a 2 by 2 matrix. Okay. And then we have to take the inverse of this particular Jacobian matrix, multiply with the this function vector at which is evaluated at the present level of iteration with the present values of the unknown variables, and so that we get the updated values. Okay. So this is a two variable problem. So for which I have just shown you how we can simplify this solution. So whenever you have this two variable problem, you may do this, that you can rearrange the equations so that you can avoid the evaluation of the inverse of a matrix. Please understand, when the systems becomes larger, we cannot do this kind of an rearrangement, and we have to have the matrix inversion of in the particular computation. So, let us do this, that we rearrange it and we get this particular Jacobian matrix. This is a function matrix and the Jacobian matrix, as I told you. So, if you take the derivative with respect to y1 and y2 for both the functions, we find we obtained this as the Jacobian. Okay. So, this is the vector of the functions. Now, let us have these initial guess values as 0.5, 0.5 as we have done for the previous way of solution by the successive substitution. So, here what we do, we evaluate the function values at these guess values, and then we also evaluate the Jacobian matrix, okay, and we put these values and we get this particular Jacobian. And now what we do, we simply plug in the values over here and we get this kind of a matrix system, and you can easily see that from your linear algebra, you know this is 2 by 1, this is 2 by 2 and this is 2 by 1. So, naturally this resulting product will be having a dimension of 2 by 1. So, this is a kind of internal check for you that you are in the right path. So, in the first iteration what we do, we simply multiply this matrix with the vector and we get this expression and this expression. Now, you can see that we have two unknowns and two linear algebraic equations, and because it is only two variable, we can easily find out the values of these two unknowns by rearrangement, and we can see that I am not going to detail of the this evaluation of this y1 y2 values, you know it quite well. So, you can see that we are getting the values of y1 and y2 like this. Okay. So, after getting these values, we can see that 0.5 we have moved up to 0.7 and for y1, and we have moved up to 0.554 for y2. Now, taking these values of y1 and y2, we again go for the next iteration. Here again we find out the function values over here, and the Jacobian we are evaluate for the new set of y1, y2. Here we get them, and again we put these values over here in this equation. Again we obtain a set of two linear algebraic equations. From these two expressions, we can find out the value of the y1 and y2. Again, you can see here that because Newton-Raphson is quite effective, if we are nearby the root, you can see that the way these two values are trying to get converged. So, this you can carry forth and to get the actual solution. Now, we come to the solution of an equation of state. This I told you separately, because in this cubic equation of state, we have to find out three values of either the compressibility factor or the volume. Okay. So, depending on the way we are rearranging the equations, and as I told you in the class that there are many cubic equations of state, like van der Waals is the first one, and then we have Peng-Robinson equation, we have Suave-Redlich-Kwong equation, so on and so forth. So, for your understanding and for demonstration purpose, we have taken a van der Waals equation of state, but this is not restricted for this particular equation of state. So, here we have that we have to find out the compressibility factor for N-butane at 1 atmosphere and 500 K using the van der Waals equation of state. Now, please understand that this even though this particular problem is asking us to find out the value of Z, but this Z value may also be used to find out the density of the particular fluid. Okay. So, we may not stop at Z. So, for demonstration purpose, we are stopping at Z. So, if you go to the van der Waals equation of state, you will find these are the values of the parameters involved in the equation, and you see that these are given in terms of the reduced pressure and reduced temperature. And what are these? These are nothing but the ratio of the actual value to the critical value. That means, if I want to find the reduced pressure, this is equal to the actual pressure divided by the critical pressure. Similarly, the reduced temperature is equal to the actual temperature divided by the critical temperature. Okay? And these critical values are dependent on the particular type of the species. So, we get these values of the critical values from the literature. Now, we can proceed with the butane. So, here we have that for butane we have this is the critical pressure and this is the critical temperature, and we find out the reduced pressure and reduced temperature values here, and what we do then we find out the values of this particular coefficients. Okay. Now, once we find the value of coefficient, we put these things in this particular expression, and we have finally this expression. Now, in the lecture what I showed you that we have this form of the equation. Based on this form of the equation, we use the Cardano's method to find out the values of the z. Okay, these three values of the z. Now, please understand these values of the z may be positive, negative or even imaginary. Okay. Now, as I explained in that lecture that we find the values of d1, d2 and d3, and then these two more parameters based on this d1, d2. So, here we see that by comparison we see that d1 is minus 1.00286 and d2 is plus 0.00824 and d3 is minus 0.0000236, and we find the values of this q and the r from these two expressions. Okay. So, we find these values of r and q, and then what we do? We find out the values of r square and q cube, and we find that r square is means satisfying the condition that it is less than the q cube, okay, as given by Cardano. So, in that case these are the solution way that we have to find out the value of the theta, that is coming in terms of cos inverse of r by under root q cube. So, we put the value of theta here, and please understand this theta is in radian. Okay. So, we put this value of theta over here, and it is in terms of radian. So, we put the value of theta over here, we find the value of z1 and then we find the value of z2 and the z3 from the expressions given by Cardano. So, we find, now summarize them, we find that we are getting these three values of the roots for the compressibility factor. So, one of them is coming to be negative and one of them is coming to be 0.99 nearby 1, and one of them is coming to be quite low. Okay. Now, you will see that if you go through the books on thermodynamics, you will find that how all these values of the compressibility factor are interpreted and are used. So, I am not going into those theories, I am stopping at the finding of the roots for the compressibility factor by using a suitable numerical method. And also please understand there are many other methods which have been proposed to solve these cubic equations of state after Cardano. So, here we have a few selective references for more detail on these particular methods. Thank you.